Welcome to solving for a series solution. So let's start off finding the general series solution about x equals 0 to x minus 1 y double prime plus y equals 0. So in this case, x equals 0 is not an ordinary point, or sorry, is an ordinary point, so it does not make x minus 1 equal to 0. So just note x equals 0 is an ordinary point. Since that P0 of x is x minus 1, and 0 minus 1 is not equal to 0. So what we're going to do is we are going to go ahead and assume that y is equal to the sum from n equals 0 to infinity of a sub n, x to the n, or you can do x minus 0, or just x to the n. And we have that y prime is the sum from n equals 1 to infinity of n times a sub n times x to the n minus 1. Y double prime, the second derivative, is the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 2. If we plug this into our equation, so plugging into our equation, we have x minus 1 multiplying the sum from n equals 2 to infinity of n times n minus 1 times a sub n times x to the n minus 2. Then we have plus the sum from n equals 1 to infinity of n times a sub n x to the n minus 1. And then we have plus the sum from n equals 0 to infinity of a sub n x to the n, and all of this is equal to 0. Just a little bit of notation. Your textbook refers to this left-hand side as Ly, linear combination of derivatives of y. So we would have here that Ly is equal to. So if you happen to see this in your textbook, in your problem statements, they're just referring to essentially the left side of the equation is what it calls Ly. If we go about sort of expand or multiplying out that x minus 1, this becomes the sum from n equals 2 to infinity of n times n minus 1 a sub n times x to the n minus 1. That's multiplying in x. Then multiplying in the negative 1, we have plus the sum from n equals 2 to infinity of negative n times n minus 1 times sorry about that, times a sub n times x to the n minus 2. Then we have plus the sum from n equals 1 to infinity of n a sub n x to the n minus 1, and then plus the sum from n equals 0 to infinity of a sub n x to the n, and this should all equal 0. So if we go about reindexing, we have one term with an exponent of n minus 2. So we are going to have to reindex that one by setting, say, j equal to n plus, j equals n minus 2. So for this one, we will set j equal to n minus 2. Then again, we have n minus 1 and n minus 1. I'll reindex that with k equals n minus 1. So we wind up looking at the sum from k equals 1 to infinity. We're just shifting by 1 here, of k plus 1 times k times a sub k plus 1 times x to the k. And we have plus the sum. Here we're shifting by 2, so we'll drop down to j equals 0 to infinity of negative j plus 2 times j plus 1 times a sub j plus 2 times x to the j. Again, shifting by 1, we're looking at the sum from k equals 1 to infinity of k plus 1 times a sub k plus 1 times x to the k. And then we have plus the sum from n equals 0 to infinity, a sub n, x to the n, and this is all set equal to 0. From here, we can go ahead and just reset all of these equal to n in terms of n instead of k and j. So we have from n equals 1 to infinity. Oh, I apologize. The third sum, we should have had from k equals 0, since shifting 1 by 1 just goes down to 0. So we have the sum from n equals 1 to infinity of n plus 1 times n times a sub n plus 1 times x to the n, plus the sum from n equals 0 to infinity of negative n plus 2 times n plus 1 times a sub n plus 2 times x to the n, then plus the sum from n equals 0 to infinity of n plus 1 times a sub n plus 1 times x to the n, plus the sum from n equals 0 to infinity of a sub n times x to the n, and all of this should add up to equal 0. I need to give myself a little more space. From here, now we do have one term which has n equals 1 instead of n equals 0. However, because we have an n plus 1 times n, adding in n equals 0 is equivalent to adding 0, right? So just a note. Starting at n equals 0, does not change the first sum. Since if we had 0 plus 1 times 0 times a sub 1 times x to the 0, this is just 0. So we would just be adding in 0. So we can go ahead and just swap this to be a 0 instead of a 1. And then we can just combine all of these. They now all go from 0 to infinity. And they all terms are multiplying in x to the n. So we can go ahead and condense that left-hand side. So this becomes the sum from n equals 0 to infinity of, we have n plus 1 times n times a sub n plus 1. Then we have minus n plus 2 times n plus 1 times a sub n plus 2. Then we have plus n plus 1 times a sub n plus 1. And then we have plus a sub n. This is the coefficient in front of x to the n, and this should all equal 0. So that means then that coefficient in front of x to the n has to equal 0 for every term, right? So this means that n plus 1 times n times a sub n plus 1 minus n plus 2 times n plus 1 times a sub n plus 2 plus n plus 1 times a sub n plus 1 plus a sub n. All of this is equal to 0. We can simplify this left-hand side. We have an n plus 1 times n times a n plus 1 and an n plus 1 times a n plus 1. This actually becomes, we have our an, then we will actually have n plus 1 squared times a sub n plus 1. And then we have minus n plus 2 times n plus 1 times a sub n plus 2 equals 0. So what we get is that we have a sub n plus 2 is equal to a sub n plus n plus 1 squared times a sub n plus 1, all divided by n plus 1 times n plus 2. And then a1 and a2, or sorry, a0 and a1 are unknown. So this is a recursive definition for all those coefficients. We could work our way through and find the first however many coefficients if we so chose in terms of a0 and a1. Next up, let's go ahead and find the solution to the IVP. The equation is the exact same equation we were just working with, x minus 1 all times y double prime plus y prime plus y equals 0, with initial condition y0 equals 1 and y prime of 0 is equal to negative 1. So we know that if y is the sum from n equals 0 to infinity of a sub n x to the n, then we have that a0 is equal to 1 and a1 is equal to negative 1. Let me just update my screen. Again, this came from the fact that we had that y of x naught should equal our a naught and y prime of x naught should equal our a1. So we found previously we found that y was equal to the sum from n equals 0 to infinity of a sub n x to the n, with we have now a0 as 1, a1 is negative 1, and then from there a sub n plus 2 was defined by a sub n plus n plus 1 squared times a sub n plus 1 all divided by n plus 1 times n plus 2. So this technique allows us to find solutions to a differential second order linear differential equation we otherwise might not know how to solve. We find series format. And so you can find the recursive version here. In some cases, you can easily sort of simplify the recursive version and just get it directly in terms of a0 and a1. In other times, it's a little more complicated. But this does allow us to find our solution. And again, we could find the first however many terms of our solution just by plugging in the values and working our way through recursively.